Hello everyone. I wanted to make a little video showing you how to use JMP Pro 16 to calculate standard normal probabilities rather than the old lookup tables. So if you launch JMP Pro 16, you'll see once you close the tip of the day, you'll be looking at the home window, and we'll go to the help menu down in sample data. Now this distribution calculator we're after is quite buried in here, so it's helpful to remember where we're going. So help sample data, and from this list of options we'll be focusing again within these teaching resources on teaching scripts, in interactive teaching modules. You'll be able to see here this distribution calculator, and that's what we want to get to. So let me just orient you to this distribution calculator so that you're familiar with it. Here we have lots of distributions that are available here to calculate probabilities from. We're going to be focusing on the normal distribution. And the standard normal distribution has a mean of 0 and standard deviation of 1, which is the default setting for this normal distribution in JMP. So I don't have to change anything on that. I can calculate probabilities that correspond to certain values along the x-axis, or I can specify areas of that density and calculate values from the x-axis on that. So we'll be able to toggle back and forth between these. In this video, we're just going to be focusing on the probability calculations. Down here in the actual calculations, we can calculate where we want that area to come from. If it's less than or equal to a value along this x-axis, one of the standard normal values. If it's greater than that value, if it's between two values, or maybe I want the tail areas outside of two values. So I can specify all of that there. So let's go ahead and look at a couple of examples here. Here I have Z is a standard normal random variable, and I want to know what's the probability that Z will be between negative 0.25 and 1.35 inclusive. That means that we'll include the qualities on those. Now, for a continuous random variable, like a standard normal random variable, the probability calculation will be the same whether I include that equality or not. So I don't really have to do anything special because I have this less than or equal to and less than or equal to. Right, so it's always helpful to draw yourself a little picture and identify the area of this distribution we're interested in. So here I'm looking at the area between negative 0.25 and 1.35. Right? That's the area that I want from that probability statement. And that's helpful for me to know, because now when I go into JMP, I can identify the correct setup for this calculation. So I'll leave it as standard normal 0, 1. I'm going to get a probability that represents an area. I'm going to choose that area to be between these 2 points that it calls Q1 and Q2. So I'll just put the lower value in here, negative 0.225 and 1.35. I can type that, right? 1.35. Right? So not only does it take in those values, but it actually shows me graphically what I've done here, so I can be assured that I'm really getting the area that I'm interested in, because it'll match what I've drawn over here. And then it reports that that probability is 0.5102. Okay, and so we don't have to do anything special or tricky as we look things up in tables. We're letting JMP do all of the heavy lifting for us. So this example sort of builds the ideas from maybe an earlier version of a table where you would look at cumulative areas in order to come up with the area you're interested in. And so it splits it up as the area that's less than 1.35, and then you get the area that's below negative 0.25, and then you could subtract those and end up getting the 0.5102. But for us, let's just use this as an example to get the area that's below 1.35. So I still have a standard normal, still want an area. I'm going to change this to less than or equal to Q. I'm going to put in 1.35 here. And I'm going to notice that this gives me a lot of my distribution here. In fact, 91.15% of the area of this distribution is below 1.35. So that's my answer there, 0.9115. And then if I want to find the area that's less than negative 0.25, I can simply type that in, and I'll notice that that gives me about 40% of the area there. And then if you take the difference between those two quantities, you end up getting the 51% of the area that we were looking for originally. Okay, let's take a look at another example here. Let's assume that the random variable z has a standard normal distribution. What's the probability that that random variable is between negative 0.85 and 1.64? So here is negative 0.85. Notice it's going to be to the left of 0 there. And here's 1.64. And again, shading the area I'm interested in tells me that I want the area between those 2 points. Right? So all I'm going to do is select this option again. Change that to negative 0.85 and change this upper bound to 1.64. Just check that that shaded region matches what I was expecting, and which it does. And now that probability you can write down that the probability that a standard normal random variable is between negative 0.85 and 1.64 is 0.7518. So just a little over 75% of the area of this standard normal distribution is between those 2 points. Right? That's my 0.7518, what we just discovered. Okay, good. Let's take a look at a few more. Assume that the random variable z has a standard normal distribution. What's the probability that z is greater than 1.1? Right, so let's find on this number line where 1.1 is. There's 1.1, and I'm going to shade the region that I'm interested in. The probability that z is greater than that. Okay, well, the values greater than 1.1 are up here in the upper tail. So I want to find how much area is above 1.1 from that particular standard normal distribution. Right, so I'll come back over here into jump, and I will select this option, x greater than q, where q is my 1.1, so I'll type that in. And that tells me, so that gives me my shaded region around 1.1, and that tells me there's 13.57% of that area. So that's equal to 0.1357 above 1.1. Okay, so here's an interesting one. What's the probability that z is greater than or equal to 1.6 or less than or equal to negative 1.6? So I'm really looking at the area of the standard normal in the tails beyond those cutoff points. And one way that we might see this written is that we'll see that the absolute value of z is greater than 1.6. So that tells me that it could be greater than 1.6 or it could be less than negative 1.6. It uses the symmetry of this normal distribution to be able to specify, you know, what's written down up here in a little bit of a shorthand way here. Okay, so just draw yourself a picture again. Here's negative 1.6, here's 1.6, and the probability that z is greater than that, well, here are the values of z that are greater than 1.6, and here are the values of z that are less than negative 1.6. So I want the areas in the tail. If I come over to my standard normal distribution and I select this radio button in the calculator, this will give me areas in the tail. So I'll specify negative 1.6 for the lower cutoff and 1.6 for the upper tail cutoff. And now I've identified these areas that correspond to that cutoff. And that tells me between those two tails, I've got about 11% of the area. So half of that is down here in the lower tail and half is up here in the upper tail because of the symmetry of that normal distribution. So this is 0.1096. And then I could indicate that between those two, that gives me that 10.96 of the area of that normal distribution. Okay, how about the probability that a standard normal random variable is less than 1.3? Well, here is my normal distribution. I'm going to find 1.3 here. That's going to be above 0. There's 1.3. And the probability that z is less than that is everything to the left here. Okay, so I'm going to keep that in mind as I select the appropriate value and probability option from JMP, and I'll put in 1.30. That gives me everything below 1.3, and that is 0.9032. And then D says, what's the probability z is less than or equal to -2 or greater than +2? So let's draw that again. Here's -2 is out here in the tail. +2 is way out here in the upper tail. And I just want those little areas that are out there beyond -2 and +2. So back over here in JMP, I'm going to use this option again to get the tail areas. Put the lower value in there for value 1 and put the larger value in for value 2. There's the tail area, and I have just under 5% there. That's equal to 0.0455. Okay, so what we've found here is these two shaded regions added together is 0.0455. It's very helpful to draw these pictures to make sure you're calculating the area you think you are. The probability that z will be between 0.4 and 1.21, right? So here's 0.4, it's on the right side of 0, and 1.21 is somewhere there. So I'm looking for this area, right, between those 2 points. So I will select from my probability options, I'll select Q1 less than X less than or equal to Q2, and I'll put in 0.4 and 1.21. And that gives me 23.14. 23.14% of the area of that distribution between those two values. Now here's an interesting one. This one's asking us the probability that z is greater than or equal to 2.09 or z is less than negative 0.54. So this is asking us for some tail values, but this is the first one we've seen where they haven't been symmetric. They haven't been the same value. And that's okay. There's no problem with that. We'll just make sure that we specify it correctly. So here's z less than, there's negative 0.54. And we want z less than that. And notice that it's strictly less than, but it doesn't matter if it was z less than or equal to negative 0.54, that would be equal to z strictly less than negative 0.54. Those two things are the same for a continuous random variable. So it's just all of that same area below negative 0.54. And then we want the area that's above 2.09. Right, so those two areas. So let's come back into jump and we will choose the option that specifies the tails. Negative 0.54 for the lower tail value and 2.09 for the upper tail value. Making sure, just double checking those. And that gives me 0.3129, which is the combined areas in those two tails. Now, obviously, you can see from this figure that those are not symmetric. So I wouldn't be able just to divide that by 2 and say that's how much is below negative 0.54 and then the same, amount being above 2.9. That doesn't work in this case. So if you were interested in how much of that 31.29% was below negative 0.54, you could just calculate that. All right, so these standard normal tables were really helpful, especially back in the day before we had software to calculate these. You could take any normal distribution with any mean and any standard deviation, and you could go through this process of standardizing them to get what their units would be from a standard normal distribution. And that meant you only needed to carry around one table, not lots of different normal distribution tables. So you could transform those using what we've got here as a z transformation and get it in terms of a standard. You take any normal distribution and get it in terms of a standard normal distribution and then look up values in that table. Now we're not terribly worried about that anymore, because what we're doing here in jump will actually calculate values from any normal distribution for us just by changing these parameters. But it's a proud tradition teaching students how to do these z transformations, so we're going to keep that up and we'll look at a couple of examples here. Now, the way that you get from what I call a general normal distribution with a mean mu and a standard deviation of sigma to a standard normal distribution is by subtracting mu from the value of x you're interested in and then dividing that difference by sigma. And that will give you what that x value, what this x value is in standard units, in the standard normal distribution line. So let's take a look at an example here. If x is a normal random variable with a mean of 70 and a standard deviation of 4, what's the probability that x will be between 71 and 74? So this is a really good practice to draw out a couple of distributions here, one that represents the original units and then one that represents the standard normal units as we change them. So if it's centered, if the normal distribution has a mean of 70, that's the center. And we want to know how much of the area of that normal distribution is between 71, which is here, and 74, which is here. So I'm looking for the area of that normal distribution between 71 and 74. So one of the things I can do is standardize this. So I'll calculate that as the probability that 71 minus mu over sigma is less than x minus mu over sigma is less than 74 minus mu over sigma. Right? So what are mu and sigma? Well, that's just the mu is just the mean of that normal distribution, and sigma is the standard deviation of that normal distribution. So I can just plug those in there. That's 71 minus 70 over 4 is less than, now this is becomes z, right? X minus mu over sigma is z, minus 74 minus 70 over sigma. Okay, so one more step here. That gives me 1/4, or 1/4 in my standard normal distribution. Oh, I can replace this with a 4. That sigma should be 4 now. So I have 4 over 4, or 1. So this is the probability that my standard normal random variable is between 0.25, which is 1/4, and 1. So in standard units, what I've done here is I found what 71 is in standard units is 0.25, and 74 in standard units is 1. Okay, so that's that area. So I can calculate that over here in JMP. Standard normal 0, 1, and I'm looking for the area between these points of 0.25 and 1. And that gives me, so visually this looks right. What I'm drawn over here, that's what I'm after. And this tells me that I have 24.26% of that area between those 2 points. Okay, now let's just check and give it the normal distribution that it came from, because we didn't need to standardize this with the software we're using. We can put in a mean of 70, standard deviation of 4. Let's try that. Mean of 70, standard deviation of 4. And then for our points now, we'll put in here just the original values. So 71 as the lower value. And it automatically checks these to make sure that the larger value isn't smaller. So maybe I need to change that one first. 74 and then 71. So it identifies that. And then it gets, for that area, 24.2426, which is the same thing that we calculated in standard units. So either way, you get to the same solution there. Okay, a couple more of examples for standardizing. Given a normally distributed population with a mean of 110 and a standard deviation of 20, find the following probabilities. So we're going to find in the first one the probability that x is greater than 110. So let's standardize that. That's the probability that x minus mu over sigma is greater than 110 minus mu is 110 over sigma is 20. So 110 minus 110 is going to be 0. Doesn't matter what the denominator is at that point. That's going to be the probability that my standard normal random variable is greater than 0, right? And we'll remember that in standard units, 0 corresponds to the mean of that distribution. So I'm really looking at all of the area that's greater than 0 in this, once I get to this standard units, standardized z-score. So that really should just be 50% of the area, because of what we know about this normal distribution. It's symmetric about the mean. The area sums to 1. So we can put that in here though and just check it out. So 0 and 1. And the probability that we're greater than 0 here is 0.5. Right? No big surprise there. In part B, we want to know the probability that x is greater than 90. So let's standardize that. The probability that x minus mu over sigma is greater than 90 minus 110 over 20. So that's the probability that a standard normal random variable is greater than negative 20 over 20. So that's the probability that a standard normal random variable is greater than negative 1. So if I get my standard z-score units down here, there's 0 and here's negative 1. So what we've determined was 90 in the original units corresponds to 1 in the standard normal units. And I want the probability x is greater than 90, and that's the same thing that z is greater than negative 1. So let's put that into our distribution calculator. I got a standard normal here greater than negative 1, and that gives me 84.13% of the area. That is greater than negative 1. And we could have gotten those same quantities just by putting in that general normal distribution centered at 110, standard deviation 20, and by giving it, if we wanted the area above 110, I can put that in there, and that gives me half of the area of that normal, or above 90, I can just change that, and that gives me the 84.13 that we saw before. Okay, and then our final example here is if we let x be normally distributed, it's a normally distributed random variable with a mean of 8 and standard deviation of 3. If a single value of x is taken from the population at random, what's the probability it will be between 10 and 13? So it's always nice to draw yourself a little picture of what's going on here. So I'm going to draw my general normal distribution centered at 8, that's its mean, and it has a standard deviation of 3. And I want to know how much area is between 10 and 13. That's the area I want to figure out. So what I can do is put this in standard units and figure out the area between the z values that correspond to 10 and 13. So the probability that x is greater than 10 but less than 13, if I am to standardize this, I'll take 10 minus 8 over 3 is less than x minus mu over sigma is less than 13 minus 8 over 3. So that is 2/3 is less than my standard normal is less than 5/3. So this becomes 2/3 is 0.66 repeated, 7 less than z, and 5/3 is 1.6667 that repeated. So what I'm looking for then is the area of a standard normal that's between 0.6 repeated and 1.66 repeated. All right, so I can come back here to my distribution calculator, make sure that I'm looking at a standard normal 0, 1, and I want the area between these two values, 0.66667 and 1.66667. So this looks like the area that we've drawn over here. That looks right. And that tells me that that probability is 0.2047 or 20.47% of the area between those 2 points. And again, we could have just skipped the standardizing if we wanted to and put a mean of 8 in there and a standard deviation of 3, and then would say give us the area between 10 and 13, and that gives us the same exact area. All right, so hopefully this is helpful. You guys can start using this JMP distribution calculator in place of the old tables that are limited in terms of what information they can contain, and really create a little bit of a diversion in terms of learning statistical concepts, in that you start learning conventions about how to read a table rather than statistical concepts that are associated with them. So I hope this gets you guys a little further down the road without having to do some of that distracting work with the tables. All right, good luck, you guys.